In the second half of section 4.6, modeling with exponential and logarithmic functions, we're going to talk about some special exponential logarithmic functions. The first one we're going to tackle is Newton's law of cooling. Newton's law of cooling basically says if you have a hot liquid like a cup of coffee and you take the coffee out of the urn, so it's now off the burner, you pour it into your cup, the longer it sits out, it's going to cool. And how fast it cools depends on the surrounding temperature. So you know that it's going to cool faster in the cold air outside than it will inside a room that's at a nice and cozy 72 degrees. In this equation for Newton's law of cooling, T of T, where capital T is temperature and little t is time, is equal to T sub S, that's the surrounding or room temperature, plus D naught. D naught's the initial difference. That's the difference between the liquid and the room temperature, e raised to the negative kt. K is going to be a constant. We may need to find it. Notice that e is raised to a negative rate. K is our rate. That's because the object, or not the object, but the liquid in question is cooling. So it's kind of like decaying. So in example 7, a cup of coffee has a temperature of 200 degrees Fahrenheit and is placed in a room that has a temperature of 70 degrees Fahrenheit. After 10 minutes, the temperature of the coffee is 150 degrees Fahrenheit. Find the temperature after 15 minutes. Well, in order to find the temperature after 15 minutes, we need to write a model for this particular function. So there are some things that I know, like I know that the initial cup of coffee is 200 degrees and it's in a room that's 70 degrees. So I need to find the initial difference. The initial difference is the initial temperature of the liquid minus the room temperature, which is going to be 130 degrees. I know the surrounding room is 70 degrees. And I do know that after 10 minutes, the temperature of the coffee is going to be 150 degrees. So I can set 150 equal to 70 plus 130e to the negative k times 10. The only thing I don't know is k. One of the things I want to remind you is you cannot add 70 and 130. That's one of the most common mistakes students make with this particular problem. We're going to solve this by subtracting 70. So I get 80 is equal to 130 e to the negative, I'm going to rate it as 10k. Before you can write this in log form, you still have to divide by 130. Now I can take the natural log of 80 over 130, and that's going to equal negative 10k. And I'm going to divide the natural log of 80 over 130 by negative 10, and I'm going to find out that k is approximately 0.04855. So now I have an equation. T of t is equal to 70 plus 130e to the negative 0.04855t. So now in order to find out the temperature of the liquid after 15 minutes, I'm going to plug 15 in place of t and evaluate in my calculator, and I'm going to find out that t is approximately 30.2 degrees. Nope, I'm sorry. Try that again. It's going to be 133 degrees Fahrenheit. What if I want to find out when the coffee will have cooled to 100 degrees Fahrenheit? In other words, when will the time make the coffee be 100? So I set 100 equal to 70 plus 130e to the negative 0.04855t, and we're going to solve that equation for t. First, I'm going to subtract 70, so I'm going to get 30 is equal to 130e to the negative 0.04855t. And then we're going to divide by 130. And then we're going to take the natural log. And then I'm going to do the natural log of 30 divided by 130. And divide that answer by negative 0.04855. 0.55, and I'm going to find out that t is approximately 30.2. What are the units of measurement here? Well, the units of measurement of time in this particular problem is minutes. We also have some logarithmic scales that pop up quite often. One of the logarithmic scales that we talked about in chemistry is the pH scale. To find the pH level of something, you do negative log of H positive, where H positive is the hydrogen ion concentration. If your pH is equal to 7, the substance is neutral. But if it's less than 7, it's an acid. And if it's greater than 7, it's a base. In example 8, the hydrogen ion concentration of a sample of human blood was measured to be 3.16 times 10 to the negative 8th moles per liter. Find the pH and classify the blood as an acid or a base. Well, all I have to do is negative log of 3.16 times 10 to the negative 8th. And when I plug that into my calculator, I get approximately 7.5. Since 7.5 is greater than 7, this is going to be a base. What if I said the most acidic rainfall ever measured occurred in Scotland in 1974? Its pH was 2.4. Find the hydrogen ion concentration. So what if, now let's do a different color. What if 2.4 is equal to negative log H positive? I want to solve for this because that's the hydrogen ion concentration. Well, the first thing I'm going to do is I'm going to multiply both sides by -1. And then I'm going to rewrite this in exponential form. Remember, this is a common logarithm, so its base is 10. So we're going to rewrite this as 10 raised to the negative 2.4 is equal to H positive. So 10 raised to the negative 2.4 in scientific notation, let's see, is going to be approximately 3.98 times 10 to the negative 3rd moles per liter. Another log scale is the Richter scale. That's the scale we use to measure the magnitude of earthquakes. The magnitude of an earthquake is equal to the log of the intensity of the earthquake, which is measured by the amplitude of a seismograph reading taken about 100 kilometers from the epicenter of the earthquake, divided by S, which is going to be the standard intensity earthquake. That's the intensity earthquake whose magnitude is actually 0. The standard earthquake is actually about 10 to the negative 4th centimeters. You wouldn't even feel that moving. In example 9, the 1906 earthquake in San Francisco had an estimated magnitude of 8.3 on the Richter scale. In the same year, a powerful earthquake occurred on the Colombia-Ecuador border that was 4 times as intense. What was the magnitude of the Colombia-Ecuador earthquake on the Richter scale? So we're going to start with the fact that the magnitude, which is the log of I over S, for San Francisco was 8.3. And we know that the magnitude of the Colombia-Ecuador earthquake was 4 times as intense, which means I'm going to multiply I by 4. I'm actually going to use our properties of exponents to separate this. 4I over S is the same as 4 times I over S. So I can rewrite this as the log of 4 plus the log of I over S. But the log of I over S is 8.3. So in order to find out the magnitude of the Colombia-Ecuador earthquake, we're going to add the log of 4 plus 8.3, which is going to be approximately 8.9. Now, you may not see the difference between 8.3 and 8.9 to be huge, but on the Richter scale, it really is. In problem number 10, the 1989 Loma Prieta earthquake that shook San Francisco had a magnitude of 7.1 on the Richter scale, how many times more intense was the 1906 earthquake than the 1989 event? So remember, we said the 1906 earthquake was 8.3 on the Richter scale. I'm going to do this different from the way the book does this because they do it in a silly method. So the magnitude, which is the log of I over S, remember, this is the intensity divided by the standard intensity. So we really don't care about the standard intensity. We're going to rewrite this problem in exponential form. Since this is a log base 10, we're going to rewrite it as 10 raised to the magnitude is equal to the intensity. So to figure out how many times more intense the earthquake in 1906 was than the one in 1989, we're going to do 10 raised to the 8.3, and we're going to divide it by 10 raised to the 7.1. When you want to find out how many times more one number is than another, you divide. We always put the bigger number on top. And if you put this in your calculator, you're going to find out it was about 16 times more intense. The last log scale that we're going to talk about is the decibel scale. That's the level of sound that we hear. So some things can be very quiet, like a butterfly's wings flapping, or something can be really loud, like a jackhammer. The equation is B is equal to 10 times the log of I over I naught, where I is the intensity of the sound level, and I naught is a barely audible sound. So I naught is going to be 10 to the negative 12th watts per meter squared. Problem number 11. Find the decibel level intensity of a jet engine during takeoff if the intensity was measured at 100 watts per meter squared. So the decibel level is going to be 10 times the log of the intensity divided by the barely audible sound. Now the nice thing about this problem is you can just shove it in your calculator to figure out what the answer is, and it should give you 140. And decibels is abbreviated little d, big B. And that is modeling exponential and logarithmic functions part 2.